Hello, in this episode we're going to be taking a look at raycasting. The Unity documentation describes it very well. A raycast is conceptually like a laser beam that is fired from a point in space along a particular direction. Any object making contact with the beam can be detected and reported. I'll give 3 common examples of where this technique is useful, although it does of course have many more applications. So in a strategy game, you might want to be able to place objects on the terrain. To do this, you can perform a raycast from the camera through the mouse position and detect the point at which the ray intersects with the ground. In a combat game, when a weapon is fired, you could cast a ray going out from the barrel of the gun in order to detect which object was hit. Finally, if you want to know whether or not an enemy is able to see a player, you could cast a ray from the enemy's position in the direction of the player and see if it reaches the player without colliding with anything else. Now, Unity of course supports raycasting in both 2 and 3 dimensions, but the implementations are slightly different, so we're going to take a look at them both, starting with the 3D version. Alright, so I have an empty scene here in Unity, and I'm going to start off by creating a new cube object, which I'm going to duplicate and move to somewhere else in the scene. And then I'll also create a new C# script called test1, which I'm going to attach to the first cube and then open up. Now, inside of the update method, we can have our raycast code. So we'll start by constructing a new ray, which you can just call ray, set this equal to new ray, and the constructor takes in a vector3 origin and a vector3 direction. So let's apply it with the position of the object to which the script is attached, as well as the forward direction of that object. Then, to store information about the raycast collision, assuming that it hit something, we'll have a raycast hit variable, which I'll call hitInfo, and we won't set this to anything because it will be the responsibility of the raycast method to actually assign to that variable. Now, if we hover over raycast hit, we can see that it's a struct, which means that it's a value type. So if we want the raycast method to be able to assign to hitInfo, hopefully you recall from last episode that means we're going to be using the out keyword. So we'll see that coming up soon. But first of all, the raycast method is a static method inside of the physics class. So we call that with physics.raycast. And as you can see from this little box here, the method returns a bool. So true if the ray hits something and false if it doesn't. And we can also see that this method accepts a variety of different parameters. If we just go through these all, you can see there are 16 variations. We'll use one of the simpler versions, just passing in ray, and then using the out keyword to give it our hitInfo variable. All right. Now, we want to know if our ray actually hit something or not, so it's quite common to surround this method call with an if statement, like so. And in here we then of course have the logic for what should happen when the ray hits something. Now, for our purposes, let's just make it draw a line from the ray origin to the hit point. So we can use the debug.drawLine method, which is just a method for drawing lines inside of the editor. The lines will never appear in a finished build of the game. As you can see, this takes in a vector3 start and a vector3 end. So let's use ray.origin as our starting point and hitInfo.point as the end position. And as a third optional parameter, we can also add in a color, so I'll just use color.red. Let's then add an else statement, so if no collision is detected, then let's say debug.drawLine from ray.origin to ray.origin plus ray.direction, and we can multiply that by whatever we want the length of the line to be, let's say 100, and we can make the color green. Now, I should mention that when we use the raycast method without a max distance parameter, then the ray is considered to go on forever. So just because I'm drawing it for only 100 units doesn't mean that the ray is only 100 units long. If we wanted to restrict it to 100 units, we could add a third parameter here, max distance, and set that to 100. Let's now save this and go into Unity and press play. So we can see a green line shooting out for 100 units there, And if we rotate this, you can see the ray updates. And of course, most interestingly, when we rotate this so that it's facing the other cube, then the line turns red and ends at the hit point. All right, let's close out of that and go back into the script and explore some of the other parameters that we can pass into the raycast method. So one thing that we can pass in is a layer mask. So let's create a layer mask variable called mask. And I'm just going to make this public so it shows up in the inspector. And we'll pass this in as our fourth parameter. All right, let's save that and go into Unity. And here we should now see that we have this mask variable in the inspector where we can select which layers the raycast should interact with. So as a quick experiment, let's create a new layer. I'll simply call this test, and I'll assign this test layer to our second cube. And let's now start up the game. So you can see the raycast doesn't interact with it now, but if we change our mask to accept the test layer, then all of a sudden it does collide with this object. Now, I should make it very clear that the ray isn't just colliding with the mesh of this object, it's colliding specifically with the collider attached to it. So if we remove the box collider from this, then the ray can no longer interact with it. So the object obviously has to have either a mesh collider or one of the primitive colliders, such as the box collider or the sphere collider, in order for raycasting to be a possibility. Now I'll re-enable this so that the raycasting works once again, and let's now examine what happens if I turn this collider into a trigger. So I'll enable isTrigger, and as you can see, the raycasting still works exactly the same. Now, depending on what you're doing, that may or may not be the behavior that you want. So happily, there's an easy way to configure this in our script. So let's head over there and add in a fifth parameter, which is query trigger interaction. So we can write query trigger interaction, and then we can choose from collide, ignore, and use global. So collide is obviously the default setting, as we saw, which does report trigger hits, and ignore never reports trigger hits. I'll show you in a moment what use global is, but let's choose ignore and save that. And now heading into Unity, I'll go into my cube and just remember to set the mask to test. So now if we play this and rotate the cube, it is colliding with the object as before, but now if we change it to isTrigger, then it no longer collides. So use global is just using whatever you have set up in your project settings over here. If you go to physics, you can see there's this little query hit triggers, and that shows that the default behavior is to use hit triggers. So going back to MonoDevelop, we have now essentially covered all of the different things that you can actually pass into the raycast method. So some of the versions of raycast will take in the position and direction of the ray as two separate parameters instead of just this one ray object, but there isn't any other type of information that you can give the raycast method. This is the lot of them. So the only other thing left to explore then is what information we have available to us in our hitInfo variable. So let's write hitInfo dot to get the full list. And you can see there's a bunch of stuff here, but the main points of interest are first of all the collider, which is obviously just a reference to the collider that was hit, and then the distance, so how far between the origin of the ray and the hit point. Then there's the normal vector of the surface that was hit, which I'll talk about in more detail in test 2 that we'll be doing in a moment, and then the actual impact point. Now, important to note is that through the collider, we can get a reference to the actual game object. So if I wanted to over here, I could say print hitinfo.collider.gameObject.name. So now if we run this, and I point this at the object, you can see it prints out cube1. And of course, if we can get a reference to the object, that also means that we can destroy the object. So let's try doing that. You can say destroy hitinfo.collider.gameObject. Or alternatively, you can also go through hitinfo.transform.gameObject. Let's save that and run this now. And so as we rotate this, as soon as it hits, the object is destroyed. Of course, with our reference to the game object, we can also get components on that game object. So we can get a script component and then call methods on that script. So in essence, we can do whatever we want with the object we've detected. Okay, that is everything that I wanted to look at for test 1. So I'm now going to save this scene and head over to a scene called test 2, which I prepared beforehand. And this scene has just got a terrain mesh with a mesh collider attached. And there's also this cube object, which I've set up so that the origin is at the base of the cube. So you can see if I rotate, then it rotates around the base. Now, let's go into our scripts and create a new C# script called test2. And what we're going to be doing in this test is recreating the first example that I described, where you're trying to place an object on a terrain. So let's create an empty game object. I'll just give this a name like object placer, and I'm going to attach the test2 script to that. Let's then open up test2, and we'll get a reference to the cube object that we're going to be placing. So let's call this object to place. And then we'll also want a reference to our game camera. So I'll make a public camera variable called game camera. Then in the update method, we're going to want a ray that goes from the camera position through the mouse position. So let's write ray. We can call this ray once again. But we don't need to configure this ourselves because the camera class actually has a very helpful method. We can write GameCamera.ScreenPointToRay, which, as the summary says here, returns a ray going from camera through a screen point. And the reason this is so helpful is that the mouse position stored in the input class is stored in pixel coordinates, which is a screen point. So if we just pass that in there, we already have our ray configured, and we can now go on to create our raycast hit variable. Once again, call this hit info, and then let's say if physics.raycast, pass in our ray and our hit info. We'll then say object to place dot position is equal to hit info dot point. Let's save that and try run this. We'll first want to assign our cube to the object to place variable and the main camera to the game camera variable. Let me just make this game window a little larger and press play. Whoa. Okay, so here we can see that our raycast is hitting the cube instead of the terrain. Now, obviously the best solution for this would be to create a layer mask and have our terrain object on a separate terrain layer, but in the interest of time, I'm simply going to disable the box collider on the cube. So now if I press play, we should be able to drag this along the surface of the terrain. Now, it would be very nice if the cube would rotate to match the contours of the terrain. So let's go back into our script and let's examine this hitinfo.normal variable. So a normal is simply a directional vector that is perpendicular to the surface of a mesh at a particular point. In this case, that point, of course, being where the ray hits the mesh. So we can use this to calculate the correct rotation of our object. Let's write object to place dot rotation is equal to, and now we'll be using a quaternion method called quaternion dot from to rotation. This takes in two vector threes, a from direction and a to direction. So we're trying to rotate from a upwards direction, so vector 3 dot up, to the direction of the surface normal, so hit info dot normal. If we save that now, go back into Unity and run this, we should see that the cube rotates to match the surface of the mesh. Just to give another example of where knowing the surface normal can be helpful, if you want a projectile to ricochet off a surface, then you can calculate the direction of the ricochet using the projectile's original direction and the normal of the surface. That's everything for test 2. In the final test, we're just going to be looking at how things differ when we're working in a 2D environment. So I'll switch over to my third scene, which is just a default empty scene. And in here, I'm going to go into 2D mode and then just create a new sprite object. We need a image here, so I'll just use one of these default UI sprites, maybe the knob. Let's press F to zoom in on that, and I'll add a circle collider to it. I'll then also duplicate this so that we have a target object, place that somewhere up there, and then going into the scripts folder, I'll create a new C# script called test3. This one we can attach to our first sprite. Let's open it up, and I'm going to delete all of the stuff we don't want. And then in the update method, let's start by examining the physics2d.raycast method. So the first thing to notice is that this one doesn't return a bool, instead it returns a raycast hit2d object. And also, it forces you to pass in a vector2 for the origin and direction. There's no version which allows us to pass in a 2D ray. So let's pass in transform.position. So even though that's a vector3, it will just take the x and y coordinates to make a vector2. And then for the direction, we'll pass in transform.right. Okay, now this returns a raycast hit 2D as we saw. So let's say raycast hit 2D hit info is equal to the raycast hit 2D returned from the method. But now, since we don't have any bool, we don't have any obvious way to determine whether or not we actually hit something. So it turns out the way to do this is to say if hitinfo.collider is not equal to null, then we know we've hit something, since otherwise there would be nothing assigned to the collider. So in that case, let's draw another line, just with debug.drawLine, going from transform.position to hitinfo.point, and let's use color.red once again. Otherwise, debug.drawLine from transform.position to transform.position plus our direction, which is transform.right, multiplied by, let's say, a length of 100, and then we can use color.green. As with the 3D version, we are of course able to pass in a max distance to the raycast method, so we could pass in 100 here if we wanted. Let's save this now and run this in Unity. So, as you can see, no line is being drawn, and the reason for this is that the ray is actually hitting the circle collider even though it started inside of that collider, and that's a big difference to the 3D version. If you remember in the first example, our ray was actually starting inside of a cube with a box collider, but it just passed straight through the box collider. Now, in the 3D version, that is the only possible behavior. We can't make it collide with a collider that it starts inside of, but with the 2D system, we can actually configure that. If we go into monodevelop, let's set this in the start method. We can write physics2d.queries start in colliders, and if we don't want it to collide with a collider that it started inside, then we can just set this equal to false. And now if we run this, you can see the green line being drawn there. And if I rotate this around, then it will turn red as it hits the other sprite. All right, so the only other things to mention about the 2D system is, first of all, as you probably noticed, physics2d.queries hit triggers also exist, so we could set that if we wanted. And then the other parameters for the raycasting are, first of all, layer mask, as with the 3D version, and then there's also a min depth and a max depth. So all that is, if I just go back into Unity, is when you're working in 2D mode, you sort which sprites appear in front of other sprites by changing their Z values. So a sprite with a lower Z value will appear in front of another sprite. So if I set this with a Z value of 0, whereas the other one has 1.3, then this one, if I drag it over, will appear on top. So the min depth and max depth just specify what range of Z values the raycast will actually interact with. And by default, the min depth is set to negative infinity and the max depth is set to positive infinity, so it will detect collisions no matter what the Z value is. But by setting that, you can make it only interact with foreground elements or background elements, and so on. Right, that is everything for this episode, so I hope you're now more comfortable with raycasting, and I'll see you in the next episode. Until then, cheers.